Hello students, let us start our session of chapter number 13, Nuclei. In each atom, at the center, nucleus is existed. In that nucleus, positive charge is concentrated. All the positive charge is concentrated in that tiny small area of nucleus. We can define that almost mass of atom is concentrated at the center of the atom, at the nucleus. The radius of the nucleus, that would be equal to radius of an atom divided by 10 raised to 4 and volume of a nucleus, that is volume of an atom divided by 10 raised to 12. By comparing its radius and volume, we can define that atom is almost the empty space, and nucleus will contain almost all the mass of an atom at the center. Now, if we want to determine the atomic mass and composition of a nucleus, for that we are taking reference as in carbon, as carbon is the most stable atom available in atmosphere around us, which is having a proton-neutron ratio 1:1. Based on its stability and a stable atomic number, we are utilizing as a carbon reference, having its mass 1.992647 into 10 raised to minus 26 kilogram. Here it is defined in kilogram, which is a very smaller, the unit in multiple of 20 minus 10 raised to minus 26. So here, for this simplicity purpose, we are using a smaller unit that is known as atomic mass unit. And one atomic mass unit equal to 1/12 times the mass of the carbon. So that would be equal to 1/12 times 1.992647 into 10 raised to minus 26 kilogram will give you 1.660539 into 10 raised to minus 27 kilogram. Here this atomic mass expressed in atomic mass unit U, which is very close to the multiple of mass of the hydrogen atom. If we want to measure the atomic mass of any atom by the device, then that device we can use as a mass spectrometer. Here in the atmosphere, we are having a different types of atoms, but a different types of atom of the same element. It means having the same atomic number. If atomic number is same, they are having a different chemical properties, but all these atoms are having different mass. So here such atomic spaces of same element having a different mass are known as isotopes. Every element consists of a mixture of these several isotopes. For example, chlorine has two isotopes having their mass 74.98 atomic unit and 36.98 atomic unit. So here, which are integral multiples of mass of the hydrogen atom. So while we want to calculate its average mass of chlorine atom, we can obtain by its weighted average we are taking. Their weighted average in the atmosphere is existed by that amount. We can take 75.4 into 34.98 plus 24.6 into 36.98 divided by 100, which is available 35.47 atomic unit. Likewise, hydrogen has three isotopes having a different mass 1.0078 unit, 2.0141 atomic unit and 3.0160 atomic unit. So here the nucleus, which is having a lightest atom, that is hydrogen, having a relative abundance 99.985%, that is a proton. So now if we want to calculate mass of proton, by the spectrometer we able to get 1.00727 atomic unit, and if we convert into the kilogram, that would be 1.67262 into 10 raised to minus 26 kilogram. And by the mathematically, if we want to get mass of proton, that would be equal to mass of hydrogen atom minus mass of electron. That would be 1.00783 atomic unit minus 0.00055 atomic unit. Here hydrogen having two isotopes which are known as deuterium and tritium. Deuterium is naturally available in atmosphere, but tritium is artificially produced in laboratories, which is unstable. Here the positive charge present in the nucleus is the protons. Protons carries the fundamental charge, which is stable. All the electrons are lying outside the nucleus. So here the atomic number, if we want to define, that is the number of electrons moving outside of the nucleus, which is denoted as Z. And electron are negatively charged, having energy minus E. So if we want to determine its total charge of atomic electrons, so charge of electron minus E into number of electrons Z. So it will give you minus ZE. Likewise, if you want to determine the charge of nucleus, so as we know in the nucleus protons are there. Number of electrons and number of protons in the atom is same. So again we can say that number of protons existed in the nucleus, that is Z. Proton is a positively charged particle, so one proton having a charge plus E. So total charge of the nucleus that can define as plus E charge of proton into Z number of protons, that would be plus ZE. By comparing the total charge of electrons and charge of nucleus, we can say that atom is neutral electrically. And number of protons in the nucleus, that is Z, which defines the atomic number. So nuclei of deuterium and tritium, which are isotopes of hydrogen, all are contain only one proton and one electron. But as their mass ratio is different, 1:2:3, so we can say that based on that, nuclei of deuterium and tritium must contain some extra neutral matter addition of the proton. So here the amount of neutral matter present in the nuclei of isotopes expressed in the unit of mass of proton, that is equal to 1 in deuterium and 2 in tritium. So this nuclei of atom contains, that is in addition of the proton in the nucleus, having a neutral matter in multiple of its basic unit. So here this hypothesis is carried out by James Chadwick, who observed the emission of neutral radiation when beryllium nuclei were bombarded with alpha particle. And this neutral radiation knock out protons from light nuclei of helium, carbon and nitrogen, and only neutral radiation known at the time, which is denoted as photons, for electromagnetic radiation. And based on the principle of conservation of energy and conservation of momentum, if neutral radiation consisted of photons, then energy of photons would have to be much higher than it is available from the bombardment of beryllium nucleum using alpha particles. So the neutral radiation consisting of new type of neutral particles, which is denoted as neutron, and from the conservation of energy and momentum, the mass of particle can be determined, that is very nearly same as the mass of proton. So mass of neutron can be denoted as 1.00866 atomic unit, that would be equal to 1.6749 into 10 raised to minus 27 kilogram. So this neutron has been invented by Chadwick, and based on the discovery of the neutron, Chadwick was awarded by the Nobel Prize in 1935. If this neutron is concentrated in the nucleus, then it would be stable, but while it is free, then it is unstable. And during this free state, it decays into a proton and neutron or antineutrino. So based on its decaying part, its mean life will be generally in range of 1000 seconds. So if we define the composition of nucleus, this can be carried out by Z defines the atomic number, that would be equal to number of protons or number of electrons. N is the neutron number, that is the number of neutrons. A is the atomic mass number, that would be equal to total number of protons Z plus total number of neutrons N. And another term is utilize nucleon, that is for proton or a neutron. So number of nucleons in an atom, that gives you the mass number A. So notation of nuclear species or nuclides can define as A, Z, A, X, as you can see over here. X define the chemical symbol of nuclides. For example, gold is denoted as 179:79 AU. AU is the chemical symbol of gold. 179 nucleons are there, in which 79 are protons and 118 are neutrons. So nuclei of isotopes of a given element can contain same number of protons, but they are having different number of neutrons. For example, 21H, that is a deuterium, that is an isotope of hydrogen having one proton and one neutron. But 31H, that is a tritium, which is isotope of hydrogen, which contains one proton and two neutrons. Element of gold, which is having a 32 isotopes, having a range of atomic mass, that is from 173 to 204. The chemical properties of elements depends on their electronic structure. The atom of isotopes having the same electronic structure, having the same chemical behavior, and they are placed in the same location in periodic table of atomic. And the atoms, the nuclides, which is having a same mass number and different atomic number. Mass number is same, but atomic numbers are different, which are known as isobars. For example, nuclides 31H tritium and 32H helium, these are isobars. And the nuclides which have the same neutron number N but a different atomic number Z, which are known as isotones. For example, 198 80Hg and 179 79 AU. Here we are going to end this session. Hope you understood. Thank you.